Alright, so in the last two videos we saw the application of the separation of variables technique to what is called the wave equation in R1 plus 1 with a finite spatial domain. What I'd like to quickly talk about here is the wave equation R2 plus 1 with finite spatial domain. So the wave equation in R2 plus 1 looks like the wave equation in one spatial domain and one temporal one spatial dimension and one temporal dimension, and so that would look something like this. But what we're going to do is we're going to introduce another spatial dimension, a y dimension. So that means that x could be from, say, 0 to L sub x, and y could be from 0 to L sub y, and t could go from 0 to infinity. We'll call this equation 1. Where this might model, or just the wave equation in one dimension of space and one dimension of time might model the ideal oscillations of an elastic string of finite length. What this models is the ideal vibrations of a rectangular ideally elastic membrane. So maybe you want to picture this table, and instead of all this dry erase paper right here, you have an elastic membrane, and what you might want to think to do is fix the edges and then pull this up and let it go down and oscillate around. That's what this equation would represent, a model. Through separation of variables, we find several ODE. One ODE looks like G double prime plus C squared lambda G is equal to 0. And this deals with the time dynamics of the shape. Then, if we keep exploring through separation of variables, and this would be done in an ordinary a course in partial differential equations, we find two primary functions that deal with the shape. There's an x function, which looks like the sine of this n pi over L sub x times x. Right, and this would be the case for fixed endpoints. And then you find capital Y of m is equal to the sine of m pi over L sub y times y, where n goes from 1 to 3 all the way out to infinity, and so does m. So, I'm not going to talk about where this is derived, but I want to talk about its use. So if you have this rectangle here, in the x dimension and the y dimension right here, and this is L sub x and this is L sub y, so for the n equal 1 case, here, what you're talking about is those n's are 1, so this function's only 0 when x is 0, so over here, or when x is equal to L sub x over here. Same thing for this y function. And so what this would represent is a time dynamic given by an oscillator with these shapes, and so this piece of elastic membrane would just go up and down and up and down. If I were to introduce this n equal 2 node right here, there would be this new region for which this sine function is 0, and it would be right here. And this part goes up, and this part goes down, up, down, up, down, up, down. There's some animated images on this blog post which show exactly that, and this feature right here is called a nodal line. There are pictures given for the higher order shapes that are created, and what you should notice is that those are all abstractions of the string case. What I want to talk about now is what happens if the geometry is a circle and not a rectangle. Well, if u of x, y is the comma t is the function that we're going to look at, well then it makes sense to look at this function as u is a function of r, theta, and t, convert it to polar. So if I have u sub xx plus u sub y, which is just the right-hand side of this wave equation, the question comes up, what does this look like in polar? Right, so maybe as an aside really quick, that means that I want to take the derivative with respect to x of a function u, which is a function of r, theta, and t. I don't see any x's explicitly, they're inside the r's and thetas, and that's a statement of multivariate chain rule. When you apply the multivariate chain rule to this set of partial derivatives, you get u sub rr plus 1 over r, u sub r plus, I think it goes like 1 over r squared, u sub theta. Let me look that up really quick. Yeah, this is actually two derivatives on theta. My mistake. So this is what the right-hand side looks like in polar coordinates. Key point. As we showed in the first video, it's possible to apply separation of variables, but now the question comes up, what does separation of variables look like in this context? If separation of variables is applied now, then the radial ODE looks like r squared times capital R double prime plus r times capital R prime plus r squared minus lambda squared times capital R is 0. Where this little r goes from 0 to the radius of the circle. This is an equation known as Bessel's equation. Where capital R is a function of little r. What you might notice about Bessel's equation here is that these are variables. They're variable coefficients, and since they are variable coefficients, exponential guessing will not work. And what that means is that we have to guess the power series solution. So without getting into the details associated with this PDE in the next video, what I'll talk about is the power series solution technique.